Well, thanks everybody for being here when you should be in motion. So this is when Carlile asked me for a tutorial. It's always easier to talk about what you've been working on lately. And so this is a project that Ciprian and I have been working for the last year to gather together a bunch of results in rigidity theory with a unifying theme and with an eye towards the application that motivated some of this research. So I'll try to balance the request for a tutorial on rigidity theory with this overall view, because the emphasis will not be on rigidity, but rather the opposite, on flexibility and how things move, okay? So here's a summary. The summary is just so that you know where I'm heading. So I need to cover the basics, especially for the students in audience. And during the basics, I'm not going to go into too many technical details. However, I will emphasize some of the subtle points in rigidity theory, some that have been discussed and rediscussed and have different meanings in different contexts. And then I'll switch immediately to motivation, just to tell you about the range of areas that generated some of these problems that this theory brings pays back to, and so on. And then I'm going to tell you about the 4 types of structure in the motion of these linkages that we are looking for, okay? So let's start with the basics. We have seen yesterday, so Philip did a nice introduction about bar and joint frameworks. It's about graphs and distances. We want, however, a precise definition of what rigid means, flexible means, and I'm going to discuss this both in the finite and in the periodic case. Then I'm going to tell you about the infamous generic concept in rigidity theory and what we call Maxwell's problem, one of the most famous open questions in the field. Then we switch to flexible frameworks and talk about the space of motions and distinguish between the infinitesimal motions and versus entire trajectories, with the goal of identifying meaningful structures in the space of all possible frameworks, all the possible motions of a framework that is flexible. So that's the overview. So let's start with the definitions. Yes, finite frameworks first. So these pictures speak for themselves. So on the left we have, and by the way, these pictures illustrate structures flexible or rigid that were well known at the peak of Industrial Revolution, 19th century in France. This is the famous Poisselier linkage that converts between circular and linear motion. And what is relevant about it is that it has a unique trajectory, so you activate that crank, and there is only one way in which it can move. And on the left, we have the Eiffel Tower as it was built, and of course, you want the Eiffel Tower to be, or bridges to be rigid and as stable as possible. So this is another more modern example, a toy that maybe you or your friends or kids played with. It's a 1 degree of freedom 3-dimensional framework. It's the famous Habermas sphere. And it has the property, again, it's a 1 degree of freedom structure. You just do one distance, you increase it, and everything moves along. So abstractly, a framework is given by a graph, finite graph in this case, along with some edge length. And the edge length can be taken from a particular realization or embedding. So a realization in particular, and we are talking now about a fixed dimension D, we map the vertices to points in that, in the R to the D, so real, we are in the real space, and so that the edge lengths are realized. And of course, immediately questions like this come up, and we've heard a lot of them during this, this workshop, whether is there any realization in that given direct dimension, and if there is one, so sometimes the space of solutions is empty, but if there is one, how many? Finitely many, infinitely many, and so on, questions of this nature. So for instance, for this graph with this edge length, we have we have one realization, but if the edge lengths do not satisfy triangle inequality, then you do the circles and realize that they don't intersect, so there is no solution over the reals. However, there is always a solution over the complex numbers. And mathematicians, in order to prove theorem or generalize or see the most general setup for the problem, sometimes it's useful to switch to the complex setting rather than the real one. But for applications and for the motivating problems, we are always in the real setting. This graph, a cycle of 4 vertices with these edge lengths, is realized by a foregone, a famous 4-bar mechanism, which doesn't have a single solution. It has a continuum of solutions. So when I look at this, this has empty, infinitely many, and this one has infinitely many solutions, realizations. And of course, the realization space, now we can define a few relevant concepts that we will use over and over and distinguish between them. I want to distinguish between realization and configuration. So the realization space will be the set of all the realizations in a fixed dimension, and this is a real algebraic variety in R to the dimension times n, yeah? So, well, being a real algebraic variety, a lot of results in real algebraic geometry are relevant and will be used for definitions, for properties, and so on. So, in particular, it's either empty or infinite, and why that? Because of isometry. So once we have a solution, we have in the plane a 3-dimensional space of solutions. And the configuration space would be if we factor by isometry. So in other words, we put in one big bucket all those that are related by congruence, by isometries, then we get the configuration space. And in practice, often we do this, and at least in 2D, we do this by grounding or pinning the framework. Yeah, so, oops, I pressed on the wrong button, of course. Okay. Good, so pinning is very much like this bridge, which if it was not pinned, it would have isometries, and that's not what we want, right? So this is rigid, this is flexible. Yeah, so there is not, we have a bunch of realizations that are not congruent. This is also flexible with 1 degree of freedom. So you hear this word 1 degree of freedom often, so we'd like to define it if we can. So, it's easy to see for those examples because of you can build them, you can parameterize them, you can write the equations. But if I give you more complex graphs in and this is a reasonable one, but they may be huge, you want to know, is it rigid, is it flexible? Can you answer this question quickly? And there are 2 aspects here. One is the graph itself, and the other is the placement, particular placement in which it lives. So our goal is to understand the configuration space, empty or not, finite or not, over the reals or over the complex number. We like to understand this topology. Why? Because if it's flexible, we would like to design trajectories. We like to move within the space, and the topology is relevant. Is it a sphere? Is it a manifold? This is something of a higher genus. In particular, is what is very relevant. Oops, is okay. It's how many components. Yes, are there particular configurations that we cannot reach by continuous motion? So they live in separate spaces, separate parts of the configuration space. And what is a rigid framework within this framework of definitions? What is a flexible one? And we would like to define these degrees of freedom. And I don't know, is this question even well posed? So we take this for granted, but I'll tell you that it's not to be taken for granted, actually. It's quite subtle from a certain point on. So topology of the configuration space, it's a difficult object to study, and there are groups of mathematicians who are passionate about this. So there are books on topological robotics, for instance, where they study in particular serial linkages and closed polygons, and you get results like this, that serial linkage, so in other words, a path, is a smooth manifold, isomorphic to the N torus, closed polygon. Well, it depends on the edge lengths. Already for closed polygons, the topology of the configuration space can be quite intricate. It can be, for instance, for 5 bar, when it's smooth, it can be a surface of one of these 0, 1 to 4 genus value, or 2 tori. And here's an example. Yeah, so this is a 4 bar linkage, and if the edge lengths are chosen in a particular way, this may align, and one particular configuration would be completely lying on one line. So I wanted to, this is not a very complicated examples, but I want to show you that simulating these motions and getting a sense of these properties is very easy when using some dynamic geometry software. I like very much Cinderella. And this allows us to visualize such motions. And for instance, when you see things disappearing here, but Cinderella continuing, the idea is that here we have real solutions to those length equations, but when it jumps here, it gets through a singularity, and then it jumps to complex solution, and Cinderella is handling complex solutions, which we do not see. And another thing that it allows us to do with this kind of implementation that I did is we can get to situations very much like this. I'm trying to get very close to this particular framework with this edge lengths, where you see how tiny the configuration space is. Yes, in fact, when the whole thing is aligned, the mechanism, the 4-bar mechanism is in fact rigid. If we have one bar that is the sum of all the others, it's only one particular realization. So you see, depending on the edge length, I may have different properties of the space. It can be isolated, one single point. We can be this curve, yes, this parameterized by one angle. And well, it doesn't look like all the angles. So it's part of the space, is just a segment of the whole circle. Okay, so that is what we mean by understanding the topology of the configuration space. So now, here's for those of you who know this and want to play a little bit. So just for the humble 4-bar linkage, depending on the edge lengths, the configuration space may be empty, maybe a single point, maybe a single circle, maybe 2 disjoint circles, maybe 2 circles meeting in one point of singularity, etc. Homework. Yeah, so it's been studied a lot. So connectivity is relevant, because if we have the configuration space is made of 2 disjoint parts, then connected components, then we want to actually talk about what we call the deformation space of a given configuration, which would be the connected component to which it belongs. That is what we are interested in. And I put this example here because it's very intriguing. So what you see here, it's a particular realization of 2 triangles and then another 2 bars over there. So this is rigid. Yeah. However, it's very symmetric, and the edge lengths have been chosen so that in fact they are equal and these are aligned. So another realization is to take half of it and flip it over. So what you see here is the same framework in another realization where this point and this point are on top of another. This edge and this edge are on top of another. This edge and this edge are on top of another. This edge and this edge are on top of another. Yeah? So now, when you look at this realization, it's obvious to you, I believe, that this one is 1 degree of freedom. Yes? So you see, we cannot talk about the degrees of freedom in general of the framework. We need to talk about the degrees of freedom of the particular deformation space of that particular framework. So in this component is rigid. It's just one point. In the other component of the realizations of the configuration space, it is flexible with 1 degree of freedom. It's a curve. Yeah? Good. So, good. So now this allows us to do the main definition. And the main definition is purely topological. Yeah? So configuration space is rigid. If it's deformation space, it's an isolated point. It's a unique point. And it's flexible otherwise. Yeah? No complications. Good. So rigid, flexible. Now, as I pointed out, the same graph with same bar lengths may have both rigid and flexible configurations. And this is not a phenomenon that is unknown, so it's relevant. For instance, chemists immediately recognize this structure, the famous cyclohexane ring, which is a well-known molecule that has 2 conformations, the chair and the boat. And the chair is rigid and the boat is flexible. And to get from one to another requires high energy, meaning that you actually stretch the bonds in order to move from one to another. So from the point of view viewed as bar and joint frameworks, in fact, this is more than bar and joint, because these are not these are revolute joints. So the angles are also fixed here. So in this case, the chair is really rigid, the other one is flexible. It's very much like the previous example that I gave you.
I'm sorry, Ileana.
Yes?
So this is the case because you have revolute joints which are fixed? Or this
The revolute joints are fixed, yes. And the angle between the joints is also fixed. Yes. You can model this as a bar and joint by putting an additional bar there, but I'm not visualizing to keep the molecular structure visible.
So if it were just a bar and joint?
If it's just bar and
then
joint,
there is something that is fixed, and then how do you get to the other configuration?
If it's just bar and joint, if I model, this is a molecule, yes. Right? And how you model the molecule is relevant. If you model the atoms as joints and the bonds as bars and view this as universal joints that have 2 degrees of freedom, then this is flexible, super flexible, yes? So, however, the proper modeling for molecules, for certain types of atoms, and carbon is one of them, is that if you have an atom of valence larger than 3, in fact, the angles are also fixed. And you can view conceptually, you attach to this molecule, you associate a graph in which you put a length constraint for bonds, but you also put a length constraint for the angle.
I was just worried that your statement had destroyed my whole knowledge of rigidity and flexibility. In fact,
no, it didn't. What I'm pointing out, and this is super relevant for when I'll get to applications, is how you model your molecules. And if you model them with bar and joints, it's one thing. If you model them with body, bar, and hinge, it's a different one. But I didn't want to get it would be too much. As you see, I have a lot of things to tell you today. Yes? Okay, but I wanted to point out that it's not just a theoretical obsession. These things appear in practice. And it's also because you and most of what I heard yesterday, it's this desire to get unique realizations. I want to point out that molecules are not so rigid, so they may be flexible, even those that you think are rigid in certain configurations. Yeah. Yes. So flexibility is my topic today, so let me talk as much as possible about flexible things. So in this context, let's talk about minimal rigidity, and a framework is a rigid framework which becomes flexible when any edge is removed. So that's minimal. So for instance, this one is minimally rigid. You remove any edge, and I just selected 2 here. By symmetry, you can remove any other. You get the 4-bar mechanism, which is flexible. You get this friend that we have seen is flexible, right? So this one is minimally rigid. And now I'm going to go directly to tell you that it's often relevant in scientific applications, in molecular applications, for people who do X-ray crystallography to talk about symmetries, and in particular periodic structures. And I'm going to introduce them immediately because I will point out along the way certain difficulties, but also advantages of moving to this setting. So here's an infinite graph. Think of this as covering a whole plane. So it's an infinite structure. And you obviously see that it is periodic, right? So, oops. Again, I'm not so used with this pointer. So, OK, so the pointer is here. So you see that this is repeating, right? So it's periodic. And the first question is, we want to know, is it rigid? Is it flexible? Yeah. So if this was a molecule, what you do, what scientists do, will try to simulate the motion, right? So simulate, and then you see that, OK, it moves, right? So it's flexible. But is this the only motion? Is this the only trajectory? We like to know how many degrees of freedom it has. And I brought this up very quickly because there is a problem. And if you spend some time, you'll see that defining rigidity and flexibility of periodic frameworks is not a trivial thing. First of all, we are dealing with an infinite graph. Yes, infinite flexibility. If you think about something like the square lattice, infinite square lattice, it's obvious that it has so many ways in which you can deform it. So the configuration space, it's infinite. Dimensional. It has infinitely many degrees of freedom, which from a computational point of view already sounds, how am I dealing with that? So we need something to be able to handle on computers. However, here's what comes to the rescue. It's one of the motivations for us for studying this comes from the following phenomenon called displacing phase transitions in crystalline matter. So this is a famous crystal. It's called the cristobalite that occurs in two distinct conformations. This is a crystal. You just see a part here. The same bond network structure is the same framework. Different positions of the atom. By the way, it's not only network structure, bond length and everything, right? So everything is maintained between these two, but there are different positions of the atoms. And what I want you to realize that compared to the previous picture, this is also periodic. So the deformation happened while maintaining the periodicity. So if this is my unit cell and I have these atoms in the unit cell, I might have here a deformed unit cell, but I'll have the same atoms representatives and the same bond representatives for the whole structure. So we are interested in modeling phenomena like this. And again, for this purpose, let me do another quick demo to show you how a periodic configuration might deform. So I'm demonstrating here also with 1 degree of freedom structure. So this is our planar crystal. The faces are colored just for ease of seeing what is going on. It's like a square lattice, but it is the unit cell, which is here. So there are two atoms, red and blue, two vertices in the unit cell. And the bonds, or the edges, are along the boundaries of the 4 bars. And this one moves with exactly 1 degree of freedom, and the configuration space is in 1-to-1 correspondence, parametrized, in other words, with the vertices with the points on this circle. Yeah? And you see it goes all the way around and changes, and this is my configuration space. Yeah, parameterized by this. Good. So here's our definition, the definition that we'll work with. And by the way, I'm not saying that studying periodic frameworks as infinite graphs is not worth it. It is. But it's a harder problem. And as a computer scientist, I like to deal with things that are amenable to finite means. And this definition that Ciprian and I came with couple of years ago is it's useful for precisely this purpose. So we will deal with periodic structure structures of rigid bars connected by joints, but they are constrained to move in such a way that the periodicity group that acts on it is preserved. Yeah, so it's not, we are not allowed to get an amorphous crystal to destroy the crystalline nature of the structure. So formally, when we talk about periodic deformations of a periodic bar and joint framework, in the finite case, we have a graph and the placement to talk about the framework. Here we have the graph together with the choice of periodicity. The choice of periodicity tells us that these two vertices are my representatives of the orbits of the equivalence classes under the action of the periodicity group. So everything that is a red point is obtained by translations. Even in the abstract graph, infinite graph, so these are in the same orbit. All the red points, all the blue points, and also the edges are color-coded so that you see how many edges there are in this abstract, what we call the quotient graphs. I'm not giving precise definitions, it's just I'm working here at the intuitive level. So once again, the description of the framework it's sufficient, it's captured by a finite set of points, which are the representatives, a finite set of edges, representative for all the periodic bonds, and lengths for them, and by the choice of the generator of the lattice. And this definition is in any dimension. So what we are looking, however, will be only deformations that preserve the periodicity under this abstract group, but the lattice itself, the length and the angle between, in general, the unit cell may deform. It's just that what is in one orbit remains in one orbit. And again, we can define the configuration space, we can define the deformation space, and the nice thing is that under this, with this definition, the deformation space is, we can say when it is rigid because we can identify when the deformation is an isolated point and otherwise is flexible. Yeah? Okay, so I want ahead to specify that choosing the periodicity group is important. So when I showed you the infinite graph without telling you which atoms are in the same orbit, it was not sufficient. So because I could choose this as the unit cell, or I can relax periodicity and have a larger unit cell. And you see here I have more vertices and more edges in the quotient graph. And they may have different rigidity properties. So it's important. So, and that is actually what triggered our interest in this topic, because various types of paradoxes appeared in the literature, and without a good mathematical definitions, you are lost and don't quite know how to address those paradoxes, those problems. So in particular, I brought this up because if we think about the square lattice and you take this as the unit cell, it will have one vertex representative and it's flexible. And it is flexible with just 1 degree of freedom, is the way the 4-bar mechanism deforms. But if you choose as unit cell this 3x3 fragment, then there are many internal deformations, whereas the rest can be repeated periodically. Yeah? So it's their periodicity, the chosen periodicity affects deeply the nature of the configuration space and the rigidity and flexibility properties in particular. Okay, so now quickly, some computational questions. How to compute a realization? Well, yeah, you can compute it in both cases. Finite or periodic, we have a quadratic system of algebraic equations. In the periodic case, we also have some equations for the generators. To decide whether a framework is rigid or flexible, we just need to look at that system of equations and decide whether it has a solution or not. And we'd like to compute the components and other topological invariants, but these are computationally very hard questions. So quickly, you can try it. Yeah, so this is something you may look at a framework like this. You write the equations. I just put generic values for the distances here, distance square, of course. And the space of all solutions, how hard it is to compute. Okay, so let me do a simpler example because that one, Mathematica stay for a while and, didn't. So I choose this one. It's trivial. You know the solutions. So this is the system of polynomials. These are 8 variables. We want to compute the space of all the solutions and look for Gröbner bases. And what you see here is just a Gröbner base for those little polynomials there. Yeah, so it's quite impressive, right? So this is a copy of a part of the previous one because I wanted to see what the variables are. And if you look at the variables appearing in each polynomial in the Gröbner basis, there are not no polynomial with just one variable, so meaning that it is not so we are not going to be able to eliminate everything. However, if I pin, so I specialize some of these variables, I pin the x and y to 0 and force this vertex to be on the x-axis, the polynomials are much simpler. The Gröbner base is much simpler. The variables in these polynomials, you see I have polynomials in just one variable that give me solutions. And in fact, the space of these solutions forms the configuration space, representative for configuration space. In fact, I can even ask Mathematica to solve it and gives me all the solutions. And there are 8 of them. So it's a finite realization space where each configuration is an isolated point, so it's rigid. Yeah? So some of these calculations can be done. Unfortunately, they can be done only for very small and trivial examples, but I wanted you to get a sense that it is a computational problem, and with more power, larger and larger examples can be worked out. Good. So now with this introduction, let's go to generic rigidity. I want to tell you about Maxwell's problem. So I refer to it as Maxwell's problem because the formulation actually can be traced to a paper of James Clerk Maxwell, the famous physicist. He wrote 2 geometry papers, and both of them play an important role in everything that I'll be talking about. And in this one from 1864 on the calculation of equilibrium and stiffness of frames, frames are frameworks, stiffness is rigidity. And he has a piece of that paper. Endpoints, he uses S. And this is the famous in general, which means generic in modern language. And there are these counts which say that in space you need, for n joints, this is the finite case, by the way, yeah? You need at least 3 n minus 6 bars in order for the framework to be stiff, to be rigid. In dimension 2, 2n minus 3 is the required count. In dimension 1, it's n minus 1. Which is essentially a tree. And this is what is required for minimal rigidity. You need more than that. Yeah, so at least this number. And of course, this example has 6 vertices, 9 edges, which is exactly 2n minus 3. And let's see. Maxwell's counts in a modern formulation can be expressed as a hereditary sparsity condition, and that acts as a necessary condition for rigidity. So here's the definition. So we have a graph with n vertices and e edges, and we say that it is dn minus d plus 1 to sparse, or Maxwell sparse in dimension d, if it has exactly that many edges, and on a subset of n prime at less than n vertices, it spans a similar count with inequality. And here should be less than or equal. For some reason, the equality disappeared in my slides, right? And this corresponds exactly with the counts in Maxwell for particular values of d, 1, 2, and 3. And where do they come from? They come from the system of equations that we have just seen. So the bar length conditions, there are dn variables, d being the dimension per vertex. These are the equations. These are the bar conditions. And they determine the vertex position up to rigid transformation. So the dimension of the rigid space of the rigid transformations is this. So we need at least that many equations to get isolated roots. If we have fewer, we'll never get. Yeah, so that is where the condition comes from. And this is the example that we worked before, and quickly you see that 9 equations, it's enough, and we expect to get a finite set of solutions, and you can get it, but not in 5 minutes in Mathematica. You may leave it overnight and have a stronger, better computer to calculate it. So now about 100 years later, Laman's paper proved that 2n sparsity is also a sufficient condition for rigidity of frameworks in a generic framework placement. And also, it's well known in the rigidity community with, by now, a lot of examples that the sparsity, Maxwell sparsity, is not sufficient in higher dimensions. And the most famous example is this double banana, which illustrates the fact that in dimension 3 and higher, you can have phenomena that don't appear in dimension 2, like this so-called implied hinge. I'll tell you more about this in a moment. But here's what I believe to be one of the most conspicuous, long-standing open problems in rigidity theory. We refer to it as Maxwell problem, is the 3D bar and joint rigidity. Can you characterize combinatorially the rigid bar and joint frameworks in dimension 3 and higher? Sparsity, 3n minus 6 sparsity, is a necessary condition, but is not sufficient. So let me quickly tell you what is known about that. So several approaches were proposed. First of all, for dimension 2, in dimension 2, there exist various equivalent proofs of Laman theorem by Lovász based on coverings, Maitroi truncations, rank functions, Lovász and Rechki, 2-3 decomposition, Tai and Crapo, and so on, inductive Henneberg constructions, and so on. And all of them have been generalized to dimension 3 and higher, and all of them have been disproved. Graver's conjecture, Dress conjecture, Henneberg conjecture, a lot of work in the 90s. In the 90s, people were still full of optimism. You could find papers that said, oh, rigidity in 3D is just around the corner. 30 plus years later, it's still not there.
What do you mean by disproved?
Disproved. You show that the particular conjecture, I'll tell you, it's a technical definition in terms of certain types of Henneberg constructions, and it's proven that those are not sufficient. Yeah, so they do not lead to everything. They don't cover all the class. Yeah, we can talk about that. That is a technical question, and I may not be able to tell you all the details. We look in the literature, I can point you to where you have to look. Yeah, but definitely you cannot, you have to be aware. This is a very difficult question. So counterexamples to the Dress conjecture, it's, to the best of my knowledge, is the latest one that was disproved about 13 years later by Jackson and Jordan. Okay, so let me tell you about some recent progress. So recent, well, I mean in the last 10 years or so. So this is work that I did with Mira Sitaram and her student Jialong Cheng, where we looked into, and we have a better understanding of the obstructions to 3D rigidity. And this is what we call the nucleation-free phenomenon, and I'll tell you in a moment. And this one also worked in the sense that knocked off some conjectured approaches. Yeah? So the challenge with the Maxwell's problem is not that there is a conjecture and people proposed a set of conditions and you want to prove them. The challenge there is that nobody came up with a set of combinatorial conditions that plausibly can lead to a proof. Yeah, so we don't even know what to prove. And everything that was proposed was knocked off. So you have to invent something else, and that has not yet been invented. So another approach is via the generalization to periodic framework, where this is work with Ciprian, and we gave a Maxwell-type combinatorial characterization for periodic graphs, bar and joint, in arbitrary dimension. Hold on, I mean, this sounds too strong. However, we have it's a stronger genericity condition. Yes, and that is a subtle thing that has to be understood. And this is a generalization in the sense that solving Maxwell's problem in the finite case appears as a special case of elimination of genericity in this periodic case. So it's not a trivial generalization. Okay, so let me tell you quickly a few things about the nucleation and hinges. So let's see. Okay, so all previously known counterexamples to 3D characterizations had some sort of implied hinges induced by nucleation. And nucleation means you have there some rigid graph, 3n minus 6, rigid like a banana is one of these, and they put together, they have this implied hinge. Yes, hinges between two bodies that allow just 1 degree of freedom rotation. And nucleation, it's something that appears when you study, for instance, proteins and or larger structures, and you want to decompose them into rigid structures. So if you are able to detect, like here in 2D, that this is the whole thing is flexible, but it decomposes into parts that are rigid clusters or rigid components. In this case, the color coding is done so that you see that there are a bunch of clusters, and there are a lot of these are edges that in themselves are a rigid body. So a framework, we say that a framework is nucleation-free if it contains no non-trivial rigid clusters. And trivial, for instance, in 2D are the bars. In 3D would be triangles or tetrahedra. Those are trivial. And if you have larger than that, you say that there is nucleation there. So the point is that nucleation-free frameworks exist in every dimension. These are the most challenging ones. Yes, because if you are able to detect the nuclei, you can replace them with smaller structures and solve an easier problem. But in the end, you'll get to some frameworks that are nucleation-free. And for those, how do you characterize those? How do you handle the rigidity? How do you characterize their rigidity? And the problem is that in dimension 2, the maximal sparse nucleation-free graphs are rigid. However, in dimension 3, it's a completely different behavior. And that's what Mira and myself studied. And also in dimension 2, they are independent. They are stress-free, whereas in dimension 3, you could have graphs that are flexible, still very much stressed. Yeah? So it's a completely different world. And with Mira and Jialong, we gave examples of 3D flexible nucleation-free. They are 3n minus 6 sparse graphs. And they are flexible, they are dependent, and we have no clue how to, we have infinite families. And neither Maxwell counts nor some sort of nucleation propagation, which was an approach proposed by Mira, will classify them. So that's one of the challenges in defining good combinatorial conditions for 3D rigidity. So implied hinges yield very strange phenomena in 3D. So for instance, the double banana is quite clear. Yeah, we have a hinge here, but look at this one, the triple banana. It has 3 bananas, these rigid bodies, but there are also, this one has not only these bananas as rigid components, there is here a triangle that has no edges in the background. They are implied. So this is a rigid component out of nowhere. There are no bonds, physical bonds that you can recognize. You have to have previously computed this and know that these are implied. And when there is no nucleation, such phenomena can happen and you don't know how to detect them a priori. Okay, so now let me tell you about the other approach with Ciprian. So this is a Maxwell type theorem. So it's a combinatorial characterization, and also it's a sparsity characterization for periodic minimally rigid bar and joint graphs. And is done in terms of what we call the quotient graph, which is the graph with one vertex for each orbit and one edge for each edge representative. And this is in general a multigraph. And if it has n vertices and dn plus d choose 2 edges, that's the count, the Maxwell count that you need. And this is the quotient graph of a generic minimally rigid periodic bar and joint framework, and the genericity here is very weird, we can discuss that in private afterwards, if it contains a subgraph of dn minus d sparsity type. Yeah? So in particular, you can, we have shown that we can reduce the Maxwell problem to this type of genericity elimination in periodic frameworks by taking a piece of the periodic graph and inserting there, this is done in 2D, but think of it in 3D, inserting there the 3 and minus 6 sparse graph that you want to decide whether it is rigid or not in the sense of finite 3D rigidity. And then you have to prove that displacement of edges is stress-free. Good luck. Okay, so it's a hard problem. We don't have a solution, but this is, to the best of our knowledge, the most promising approach so far. Not that we have a solution. So let me now move to flexible frameworks. So what is a flex? It's a trajectory. So you have a graph with a placement or a realization, and the trajectory, it's a curve that contains p. So it's something you can parameterize by time, so that at time t0, you have your particular configuration. And the flex exists if and only if the graph is not rigid, and it's known, because we are sitting on an algebraic variety, that if a flex exists, then an analytic flex exists, meaning that we can differentiate, so we can look at tangents. We can we can use linear algebra. So if we write the edge length equations and we take the first derivative in terms of time, then denote by vi the infinitesimal velocity, so the derivative at time 0, they satisfy linear system. And if we want to eliminate trivial motions and so on, we pin down some equations. So this is, I'm going to speed up here because this is well known. But the infinitesimal motion of a framework at a particular placement would be an assignment of velocity or infinitesimal motion to each vertex that satisfies the same equations as the tangents in P to a flex. Yeah? So we have these equations, and the flex is, the infinitesimal motion is non-trivial if it's not a infinitesimal rigid motion. And we say that, oh, and also, if a framework is flexible, then always there exists a non-trivial infinitesimal motion, but the opposite is not always true. You may have infinitesimal motion, but the framework itself may be rigid. So this is easier to compute than Gröbner basis and other complicated things. However, it does not always give you the answer. So infinitesimal rigidity, as now we have another area, instead of talking about rigidity, we talk about infinitesimal rigidity of a particular framework, and we say that it's infinitesimally rigid if it has no non-trivial infinitesimal motions, otherwise it's infinitesimally flexible. This is rigid, this is infinitesimally flexible, and these are possible velocity assignments. So these are well-known implications. Something is infinitesimally rigid, it implies that it's rigid. If it is flexible, then it's infinitesimally flexible, but the opposite directions don't work. And there exist rigid but not infinitesimally rigid frameworks. So for instance, this one is in a particular realization where these edges meet in one point, is rigid but has an infinitesimal deformation, infinitesimal velocity assignment. Now, computationally speaking, now we are on better terrain. To compute infinitesimal motions, we find solutions to a linear system. It's much easier to compute. To compute infinitesimal degrees of freedom, we compute the rank of the rigidity matrix, which is the next object. So you set up a matrix, and it's not one of Abdo's matrices, but it's in that category of techniques that are very powerful and work very well and beaten to death, and they work in any dimension. So infinitesimal rigidity can be decided for any dimension, except that there are limits to the application by the size, yes, and by the numerics. So the infinitesimal motions, in other words, are solutions to this homogeneous system. So the velocity is in the kernel of the rigidity matrix, and something is infinitesimal rigid in 2D if it is the rank is 2n minus 3, but we can say more, and that's why I wanted to get quickly to combinatorial rigidity. So Maxwell-Laman's theorem gives a combinatorial way of deciding minimal infinitesimal rigidity of a graph for almost all of this realization. In other words, generically. And I'm not going to define exactly what generic is. We can discuss this in private because it's technical. But the 2n minus 3 sparsity has good properties. It's matroidal, and it can be checked fast by combinatorial algorithms. And we heard yesterday about the approaches pioneered by Hendrickson based on matching, network flow. Network flow comes from other people. But anyway, the paper game of Hendrickson and Jacobs gained popularity because it's so easy to implement and it's so nicely looking. But I'm not going to cover it today. Okay? So generically rigid. Very quickly, we say that a graph is generically rigid in some dimension if there are frameworks which are rigid on an open dense neighborhood. Let's stay for the moment with this definition. And let me skip quickly through this. I believe that most of the people in the audience have seen these examples, and I want to get to the more interesting part a little later while I still have time. So we covered the basics, yeah? So what I wanted to say until now is that each technique, algebra, linear algebra, combinatorial, the first one is the most powerful, but is hopeless combinatorially. The other two are feasible computationally, but they don't always give you the correct solution. So now, our goal right now is to identify meaningful structures in the space of all possible motions of flexible frameworks. So let's move away now from rigidity to flexibility. So there are 4 types of structures that I want to identify. I'm going to talk about degrees of freedom, about collective motions, like rigid components, about expansive motions, and in the periodic setting about auxetic motions. And that's where I would like to have at least 15 minutes to talk. So let me just check how much time I have, because in the next 5 minutes, I'm going to go quickly over the motivation. And this is real motivation. Everything that I'm going to talk about in these few slides are problems that are applied, that I heard about them, and I'm working on them, or I've been working on them. So number 1, robots and robot arms. So for instance, something like this. This is Canada arm. It's it's on the International Space Station, and it's a linkage with rigid bars with revolute joints, by the way, and and it's used to move. How do you compute the proper trajectory so that it performs a certain task? Of course, that's where flexibility, understanding the space of motions, is relevant. Inspired by robot arms, I learned many years ago that proteins have a backbone, and the bonds there are connected by revolute joints. They are essentially robot arms at the nano level, but they are humongous. Canada arm has maybe 6 or 7 bars. This one can have hundreds, thousands, hundreds of thousands of these links. So robots don't have to be just serial. So for instance, this one is more like a tree. And you see that you have to design complex motions for it, like we design motions for us when we move. And again, the analogy is not just to show you this cute robot here, but it's also because a protein chain is not just the backbone, but it has little residues that look like little trees hanging out of each C-alpha atom. So it's more like the Aldebaran robot with a lot of trees hanging out. However, it's more because their protein structure is held in place by extra bonds, like extra interactions, hydrophobic interactions, hydrogen bonds, and so on. So we do not have only a serial structure. We have more like this, and I apologize for this. This is a bad video, but it's the only one that I could find to demonstrate this, is the Asimo robot, which is a robot that carries a tray. So you see there is a cycle there that is being formed. So how do you design the motion so that the arms don't cross, don't go through each other? So it is an interesting problem how we design these trajectories. So let's move from the macro level to nanostructures, because where there is matter, there is geometry and kinematics. And I love this quotation. I use it wherever I can. And talk a little bit about motion at the molecular level. So you may have seen this very nice animation of animations of unseeable biology. These are well-known molecular motors, they are called. So the kinesin and dynein that work on the microtubules in the cell, and they perform various functions. And what you see here is not, it's an artist's view of how they might possibly work, and there are whole labs that try to understand the emotions. My work is more at the level of understanding the particular pieces. What is their flexibility? What makes them flexible, and how is their motion designed? So, which takes me to the protein flexibility topic. We are here at the protein data bank. It's in another building. I checked yesterday. There were about 153,000 structures. This started about 40 years ago with 7 structures, out of which the first few got a Nobel Prize each. And last year, when I gave a similar talk, there were about 145,000, and the year before, 130. So it grows fast with about 10 to 15,000 structures per year. And these proteins in the data bank we have seen yesterday, some of them in your presentation, they were all tiny, but in general, even the tiniest of them are quite large. So myoglobin and hemoglobin are the ones that got the first Nobel Prize, where some of the first that were solved. 155, I think you talked something about 20 residues or so on which you can do molecular simulations. So we are interested in understanding the rigidity and flexibility of this for the following reasons. The proteins are dynamic molecules. We get them in the protein data bank in one configuration. We like to understand how they move without performing those costly, expensive, time-consuming molecular simulations that we have heard about yesterday. So the molecular dynamic simulations are impractically slow for large molecules or on a large scale. And we have seen a version of this, but what is doable with molecular dynamic simulations is essentially at the level of local motions up to here, I guess. Whereas we are interested in domain motions, subunit motions, and of course, ultimately folding. But it is here primarily that our work might be helpful. So we want to predict motions from the available static structures. Namely, we'd like to, in order to do slow motions, you have to do some sort of coarse graining. And techniques for coarse graining are those that identify representatives for subset of atoms and run the simulation using one of the representatives. And there are a number of ways of doing this. Some have been around for decades. And the recent one that was pioneered by the group of Mike Thorpe, to the best of my knowledge, is based on rigid components. And there have been software developed in his group. And in my group, we have developed software for studying mechanical properties of proteins with the goal of understanding their rigidity, flexibility, and motion, and with the goal of working possibly on all of them. So let's see what the challenges are. So here's a rigid cluster decomposition in 3D. So this is, I think it's lysozyme or something, and this is a possible decomposition that you'll see. You'll see that it has a large domain that moves as a collective, moves collectively, several other medium, and a lot of hairs that fluctuate, if you want. So it gives you insight into the potential motion of that static structure. So the Kinari 2 project, which is ongoing, has a component for biomolecules and a component for crystals. In particular, in terms of biomolecules, one of our goals is to be able to simulate, to understand the flexibility of large structures, such as viruses. So this is largest in the protein data bank is the HIV virus capsid. It's approximately 2.5 million atoms, huge number of residues. This is a smaller one, CCMV. And I'm showing this because here's a cryo-EM image of this. And it shows obviously that this is flexible. In fact, that's how it performs its function, by releasing the nucleic acid from inside when infecting the cell. And this is an engineer's model where parts of the virus are replaced by rigid components. We like to see whether we can identify the rigid components automatically and on a large scale. And finally, the last part of our application area is on crystals. And I mean not only two-dimensional crystals like graphene, but also the cristobalite that I mentioned before. We'd like to understand displacement phase transitions. Is this actually, this is high energy transition, we know. So it's very likely these are in different components of the configuration space. But there are situations, and I'm pointing here to a paper of Pauling from 1930, where he observes that in sodalite, this framework, while it is strong, actually it has deformations. He observed that about 100 years ago, that the framework collapses. That's the terminology for saying that it is flexible. So, and finally, this leads us to the topic of auxetic metamaterials. And metamaterials are materials that may exist in nature, but very rarely, and are mostly engineered to have properties that are counterintuitive, that are properties that are not so frequent in nature. And this particular one is very weird. So here's intuitively what it says. If I take this structure here and I pull, this is the usual behavior. You pull and you expect it to become thinner. And this is a model. So you think of being a periodic structure. It's a crystal behind. And when you pull in one direction, it becomes thinner in the other direction. And as opposed to this one, oops, unusual behavior, you pull and it becomes larger, thicker. The growth there is not so striking, but here's the underlying structure, a model underlying structure that exhibits that. You see, it's the same connectivity, it's the same infinite graph in both cases, but it's with a different placement. So at the molecular level, this is the cristobalite, and this is a simulation that claims to be a model of what the transition could have happened from this state to that state, okay? Good, so now with this motivation, let me move towards the structures. Okay, quickly. I think I have about 10 minutes, yeah? Degrees of freedom. 1 degree of freedom, post-cellular linkage, we have seen it. Yes, 1 degree of freedom. So rigid and 1 degree of freedom are easy to state, easy to understand. One is an isolated point, the other is a curve. It's well defined. But what does it mean when you have more degrees of freedom, right? So when the framework is something like this one has 1 degree of freedom, I'm in the plane now. So now this is a 6-bar mechanism. I informally say it has 3 degrees of freedom. What do I mean? Do I mean the dimension of the configuration space? Can I define it in that way? Yes, so can we define it? It's in fact well posed, this question. And I want to alert you to the fact that in general, it's a trap here. And the trap comes from the existence of something. I don't know how many people have heard about kinematotropic linkages. Yeah, I was hoping that I'm bringing you something that you have not heard, because I heard about this in an engineering, mechanical engineering context. And this is an example of Wunderlich from 1954. And this is a planar mechanism. that in a part of the configuration space, it moves like a 1 degree of freedom structure, and then it reaches a singularity and goes into another part of a configuration space where it has 2 degrees of freedom. Yes? So I cannot define the dimension of the component of the configuration space. Yeah? So it's weird. I just wanted to alert you that it's subtle. However, here's another situation where we have to be careful, and that's one reason that I emphasized earlier that you have to specify for an infinite framework what is the periodicity that you are working with, because if we work with this relaxation of periodicity, we have more degrees of freedom than the one that comes if we work with this periodicity. Yeah? So degrees of freedom in the finite or in the periodic case, you have to be careful how you define them in order to calculate them. Okay. Then, however, now here's the good thing. As always, generic is nice. For generic sparse 2D frameworks, the degrees of freedom can be defined easily, and that is a correct definition. So if you have a generic structure, the 2n minus 3 minus the number of edges, so the slack up to the Maxwell-Laman count is the number of degrees of freedom, and that is what allows me to say that this one has 3 degrees of freedom in its generic position. So now let's move to the next structure that we like to find in motion, collective motion. What I mean by that. So let me show you a little motion of this framework, right? So it moves. And as it moves, it's sort of obvious that some parts move together. So let's color them. So now you see more clearly that this part moves together. That's what we call collective motions. And in 2D, these are the rigid components. In 3D are the rigid components of the structure that moves. So our protein project is, in fact, identifying the potential for collective motions. And here are quickly 2 applications. This can be used to predict the effect of ligand binding. So for instance, this was work done in Mike Thorpe's group. So with the ligand and without the ligand, the rigidity obviously changes, and meaning that we can infer functional information from the structure, namely from the structure existing in the protein data bank. This is another application where we performed a mutation that changed the number of hydrogen bonds, and that changed split this big cluster into smaller cluster, meaning that there is more flexibility here. Again, it's a functional change that was captured. It's an effect of the mutation that led to a functional change, and so that's what we can infer by this kind of analysis. So let me move now to the more involved part of structure in motion. So let's go back to this Asimo robot that moves its arms in such a way that performs a certain task. We can abstract it as a polygonal chain. So let's be in 2D. And the goal is to bring it to a certain standard position without collision, so that so we'd like to design such a trajectory. And here's one, yeah? So here's one. So when you look at it, it's not obvious what I'm doing, but there is a trajectory. So let me tell you what is the hidden structure behind this reconfiguration, behind this motion. So this one, I already told you, it has 6 bars. It has, it has 7 bars. It has 4 degrees of freedom. So generically, it lacks 4 bars from being rigid. Why not put them back? I put them in a certain way, yeah? And then I'm taking one out. I get a 1 degree of freedom. I get something that moves with exactly along one trajectory. And I'm going to move it along that trajectory until it aligns here. But since it aligns, let me freeze this joint, right? So it's the Asimo robot moves, and then this arm, well, alignment actually it's a singularity for the robot. It starts shaking. You freeze it there. Let's put it this way. So now you get, instead of 2 bars, you froze them into 1. You have only 3 degrees of freedom, and again, you can remove 1 bar and continue the motion, and so on until you are where you are. And the property of this is that this motion is non-colliding, and it's Why is non-colliding? Because the pairwise distances between vertices never decrease. They always increase, and when things increase, they never collide, right? So here's a 4-bar mechanism where it is expansive until it reaches a point from which point it stops being expansive. Certain things may get together, collision may be possible. So there is a combinatorial structure behind, so that's the structure that I was referring to. It's combinatorial behind this motion, and it's captured by this object called a pseudo-triangle. And let me not get into the details, but this is an object that you can design by playing a game where you place bars randomly with the only condition of maintaining an angle larger than pi at each vertex and avoiding crossings. And when you are done, the faces of this structure are pseudo-triangles. So the structure of expansive motion is captured by this fact that a pseudo-triangulation is always minimally rigid. It is when you remove an edge, it is a 1 degree of freedom mechanism, and it always moves expansively, and it moves without going through singularities. So we have full understanding of its degrees of freedom and of its kinematic behavior. Okay, so that's what it does here until it stops being expansive. So let me skip this because I see Carlile getting nervous, and it's 13, so I'm over time, or I have 2 minutes? Good, 2 minutes. Periodic structures, right? Auxetic deformations. I'm going to go very quickly now. You have seen this. So the point is that we have generalized the pseudo-triangulations from the finite to the periodic case, and they have similar properties. They are 1 degree of freedom and move expansively. And expansive implies auxetic, implies that it enlarges when you stretch something. And at some point, so that's a theorem. And all I want to tell you is that Maxwell comes back again because the proof of this theorem of understanding the properties of periodic pseudo-triangulations was done by using a generalization of Maxwell's theorem, the second paper, geometric paper of Maxwell, from the finite setting to a periodic setting, and is related to periodic stress and liftings. If you are curious, we can talk more about that. So let me quickly skip this. And final thing I wanted to tell you is that expansive is a very strong condition. Auxetic may not need that strength. And here we have 3 definitions of auxetics. One of them actually is very similar to causal lines in relativity, but it's just a coincidence. And we have, based on that, we can decide whether a framework has auxetic properties using semi-definite programming. I just wanted to mention the keywords to show that there are connections with everything that happened in this community in these 3 days. And then detecting auxetic deformations. Well, I don't have time, but I have a nice Cinderella demo that shows that I can detect auxeticity not only at the infinitesimal level, but on a large-scale motion by tracing certain ellipsoids and hyperboloids, certain conics through the motion. So into D will be an ellipse versus a hyperbola. And when that ellipse is present, we know that the motion is auxetic, and when it turns into a hyperbola, it's no longer auxetic. And so I'm going to finish with this beautiful quartz that looks very rigid, but when we make a framework out of it and allow the atoms to rotate, the oxygen atoms, then it has a sort of auxetic behavior. Yeah, and that's a small interval of auxeticity. And what we are doing with a colleague in a mechanical engineer material science lab, we are trying to build 3D printing models of this. Yeah, so manufacture materials. And I'm done. I'm speechless. I need some water. Okay, guess.
Questions?
Oops.
Yes, one small question. Are there conditions where infinitesimal rigidity is equivalent to rigidity?
Infinitesimal rigidity is equivalent to rigidity?
No, I mean, are there conditions where, like, are there some cases where they are...
They're equivalent.
Yeah.
Yes. To the best of my knowledge, the only cases that I know of, pseudo-triangulations are always infinitesimally rigid and have no singularities. And so it means that you infer rigidity from infinitesimal.
Okay.
And you do this by applying Maxwell theorem, showing non-existence of stress. The other famous example that I know is Cauchy theorem for convex polyhedra, triangulated convex polyhedra. They have 3 and -6 edges, and if the polyhedral surface is topologically a sphere and is convex, Cauchy theorem says this is always rigid. If it's not convex, it can be flexible, famous example of Connolly. So these are two standard examples. There are not many other known. Yes, where you can guarantee from the combinatorics that infinitesimal rigidity implies rigidity.
Well, because if there are some combinatorial conditions or what that are very easy to verify, then you can verify infinitesimal rigidity to go to rigidity. I mean, like to identify substructures that would be rigid than computational calculation.
Yeah, I mean, that's what we do, right? So it's, okay, let me phrase it this way. In dimension 2, you verify generic rigidity, you verify combinatorially. Then, if you want to make sure that really your placement is good, you do infinitesimal. And if it passes that test, you know you are rigid. And if it doesn't pass the test, then good luck with Grabner basis. Wait for a few months, and maybe you can find the answer. So that's a hard question. In dimension 3, what we have done with proteins, we also have a version of the Pebble game for bar and joint and hinge, because we cannot use bar and joint because we do not have a characterization, a Maxwell characterization there. So that doesn't work. So, but proteins are special. They can be modeled in this way. And so we do the combinatorics. And if you are lucky there, good luck with a few thousand atoms to check the linear algebra. Good luck. Yeah. So, and then what about viral capsids? Forget about it.
You mentioned that sometimes mathematicians use complex numbers even when we can't visualize the realizations. What do they use it for? What is
proofs. For proofs.
Right, but can you cite like a paper where you've seen a creative use of complex realizations?
Yes. Yes. So this is, it's easier for me to cite my papers, if you don't mind. Yeah. So this is a paper with Ciprian. In fact, it's Ciprian who is an algebraic geometer, and he converted me to this point of view. And it is the paper that counts the number of realizations of minimally rigid graphs. Okay. And the bound, so we have an upper bound and lower bounds, and the upper bound comes from viewing the configuration space over the complex numbers, because that's where the algebraic geometers have theorems and can give bounds.
Okay.
Yeah.
And
So that's one example.
This is published on what journal?
You find it on my webpage. And there are groups of people now working on these problems. The group of Chico in Linz, they have improved some of these bounds with new techniques. The group in England, Owen and Jackson, they are working with complex numbers. So there are a number of people who are using this.
Some words of a type.
For my paper, it's number of embeddings of minimally rigid graphs. On my website, it's one of the papers.
Thank you.
More questions for the coffee? Yes.
Probably a very basic question for this community. What is the complexity of testing rigidity? So I don't know.
In dimension 2, it's n squared finding rigid components, theoretically it's n cube, I think, n square. Anyway, it's in that order, but in the practical implementation seems to be behaving much better. But that's the combinatorial part. If you want to test infinitesimal rigidity, is the complexity of finding the rank of a matrix, Gaussian elimination, n cube. If you want to find rigidity using Grobner basis, good luck, super exponential. Yeah, so these are the levels of complexity. In dimension 3, there is no combinatorial characterization, meaning that you only can rely on linear algebra or never will work algebraic Grobner basis approaches. But linear algebra, that's the one that you can rely on. Linear algebra in cube.
If you ask the decision question, I give you a bunch of points in R3. And the question is there another realization? Which is not a rotation, but a non-trivial different realization.
You mean you give a bunch of points with given bars, with given length?
Yeah, I just give you the points.
Yeah, you give the, oh, you know the distance. You have the complete graph. I'm not sure what is your question.
Is there a different realization?
A different realization of what? Of the same length?
Of the same length.
If it's the complete graph, then it's rigid. The complete graph is rigid if you have all the distances.
For any set of distances?
Sorry, you gave me the points, so I have the distances.
But you probably need some missing, there are some missing distances.
Well, if there are some missing distances, then we are in the realm of rigidity. Then you have a subgraph of the complete graph, and there indeed, yes, it depends on the dimension in which you are. And if you are lucky to be in dimension 2, like you do sensor networks on a surface or something, then you can apply results from combinatorial rigidity in dimension 2.
But these examples you had, where the graph was flexible, right? So there was one configuration, you could change it to get another.
Yes.
So suppose I give you one of them.
Yes.
So now you know all the distances, but there is another one. So it's
Oh,
not
yes,
fixed,
yes,
right?
yes, yes, yes.
So
So,
that's what I'm asking. So
yes, yes. So this is the, this has been the topic of yesterday and the day before in the context of, for instance, global rigidity. If the graph is globally rigid, then your realization is unique and is the one that you have. If it is rigid but not globally rigid, then you will have other realizations. If you want to find the other realizations, then, well, generally speaking, you have to solve a system of equations, of quadratic equations. And that is in general hard, but for certain families of graphs, like the talks yesterday, you can solve the problem. So it depends on the problem. Generally speaking, it's a hard computational problem.
You can also use semi-definite programming.
Yes, okay, but okay.
But even if the dimension is so you get the realization.
No.
So I guess I'm asking is the complexity of the complementarities.
Yes.
Okay, I think with coffee,